We're brought to you by Hawaii Tracker, hawaiitracker.com. Giving you guys an update here on day 8, December 28th, 2020, of the Kīlauea summit eruption, which is still ongoing. So thank you guys for joining in. Thanks for tuning in to our updates. We're going to present to you guys information that comes from the USGS. This is a lot of their imagery, monitoring signals, that kind of thing. And then we just like to kind of point out some of the details that maybe not everyone catches going through the first time around, and kind of put it all together and hopefully try to get it to make sense for you guys. So I'll be doing more of the presenting of the images, and Dane is going to be monitoring the feeds up here. So if you guys want to jump in the chat and ask any questions or anything like that, yeah, feel free to do that, and Dane will pop in and relay that to us as we go along. So all right, guys, we'll get started here by looking at the latest video released by the USGS, and I'll start it over here a little back to the beginning. But what we're looking at here is that inner pit of Halemaʻumaʻu, which is that Halemaʻumaʻu, people have asked, is a name for this big pit which exists inside of the volcano of Kīlauea, right? So Kīlauea is its own shield volcano. It has its summit, a summit caldera, and inside the summit caldera is this pit, which is called Halemaʻumaʻu. And this pit has changed in its shape and its character over the centuries. We've been presenting to you guys some of the different views, and whether it's through paintings or photographs or maps of, how we've seen things like islands floating inside of lava lakes that have crusts over them before in the past. And so that's what we're kind of bringing an update to you guys here on the 8th day of this ongoing eruption. We mentioned to you guys in earlier first updates that following the 1924 collapse of the volcano, we had something like 10 eruptions in 10 years, 7 eruptions in 10 years that refilled that inner pit. And on average, those eruptions were about 2 weeks long. And so we're seeing a change in the character of the eruption here a little bit, because it seems like the amount of lava that's coming out is going down. The place where it's coming out of changed. Maybe that's got something to do with why it's going down. And so kind of all together, we're not surprised to see like a change in eruption. And the question really is, how long is it going to go on from this point, right? So you might imagine that, if we're going for our most probable statistics, it's only one event, 1924. I give you that. There were collapses earlier in the 1800s that we've also discussed that we just don't have that kind of information for. So, but based on what we do know, and very good records taken by Thomas Jagger, founder of the Hawaiian Volcano Observatory, back in this era of the 1920s, really reveal how that change happened, right? And it really was about 14 days average. So here we have our northern vent of our current eruption, and our western vent over here of our current eruption. And this is the one that's taken over in the last few days here, as the lava level had come up and essentially drowned, right? Started backflowing into the place where the lava was coming out before. And sometimes you have enough vigor in an eruption that the gas coming out can really bubble its way through and out, and kind of start and stop and enter, kind of you have a different dynamic of eruption that way. And we've brought up the eruption of Kīlauea in the past as an example of that. But we didn't really see that happening here. Instead, what we saw happening was that other finger of the eruption, right? And so these eruptions often come up from some source underground, some big chamber. They come up as a blade, and that blade is connected at depth, but it has different fingers, right? So we actually had our northern vent, our middle vent, and our western vent. And so the middle vent shut off early on. It may be bubbling under the lake or draining, we have no idea. That northern vent was that one that was the most vigorous. And then once that one got plugged by the backflow, it seemed like, at least, it was kind of the same time as that happened, we saw a switch to the western vent. And the western vent's now the one that's putting out the lava. And so the amounts of lava that coming out of the western vent have increased. And that was after the day before that actually switchover happened. That western vent had been completely inactive as far as lava coming out of it. There was glow and gas and that kind of stuff still coming out. So it's obviously still an open pathway, but it wasn't the easiest pathway out, right? So it became more of a chimney, while that northern vent, which now in this image here, you can really just tell by this amount of lava spatter that's here on the sides of the vent, right? You can't really see any activity, even any gas coming out of there anymore. Right, so all the gas is now coming out of this western vent over here. So this is the image from the video we have from USGS. You can kind of see here's that kind of smaller islands. There's one, there's another. These kind of higher chunks that are sticking above that lava lake surface, right? And in the daytime, you just see the silvery crust all through here, and that's the actual lava lake surface. It's all fluid and liquid underneath there, but because it's exposed to the atmosphere, the air, the colder air, imagine even this lava is coming out, on the order of 1200 Celsius, more or less, right? It kind of varies. Usually, it might be 1140, 1160, 1120. There's a ranges depending on eruption, and that tells us more about the magma. But I haven't seen that detail of reporting a temperature yet. And obviously, it's because it's hard to get there. It's hard to get any sample. There's no sample of the thing up unless the actual wind wafts up some piece of spun glass that's going to come out. You can measure the gases, because they're flying through the air. But it's really hard to get a sample of what's going on in there, to get any crystals and kind of get any kind of magma history of what's happening within that pit. So, yeah, let's move on from the video here. I'll show you some different views of this thing. So here's here's the webcam. This is all from the USGS webpage. Let me refresh it here so we can get the most current view. We can see as we approach 3:30 p.m. here in Hawaii, we see the west sun is putting the shadows. The tripods these guys are using to measure the distance to the surface of the lava lake to then give us a lava lake depth, all those other kind of things, the gases and everything that they basically can, is all being manned from the upper rim here, looking down into the pit. Right, so from this angle, that western vent is almost straight below. Right, one of these could be the webcam as well. A couple of the webcams, they're also nearby as well. So it's kind of a straight down view, and now you can see the gas coming up is really coming right at these guys, unfortunately. So it'll be a place that for these guys to be working. I'm sure they have gas masks nearby, so that they can actually be prepared for any sudden change in the direction of the wind, right? And as you guys could imagine, all the fog that's covering the entire island is coming from this one source right in here. So it doesn't look like a whole huge area of it, but it's extremely concentrated, and that's why you want to be extra careful the closer you are to the actual source of the gas right here. So that's the west cam. I'll kind of just scroll down so you can kind of get a view from the east cam. There's really nothing happening in any of this other part of the caldera. Everything over there is quiet, right? You can kind of see from the overlooks are more or less in this area. You can kind of look, and you can't really see the lava directly. Visitors have been coming and seeing the glow in the evening, and especially the glow reflecting off of the gas clouds that are rising up into the atmosphere. So in this kind of wider view here, the wide angle, you see the gas cloud here a little bit better. Right, there it is. All right, so latest thermal image. The latest image is a little bit blurry right in here. I'm not sure that's, if I had to guess, because that gas is blowing straight over that thermal camera right now, and it's having to look through that gas plume to try to see what's happening at that thermal behind there. But just an idea. We'll have to wait to see if USGS can confirm that, and nothing really here. And these other webcams. So I'm going to read to you guys the latest updates. Our last update to you guys was a couple of days ago, so I'm going to review 2 days of updates here. So this is from yesterday, Sunday, December 27th, and we are still at level watch, aviation orange. And essentially, there's not much change. Lava activities confined to Halema, with lava erupting from a vent on the northwest side of the crater. As of 7 a.m. this morning, December 27th, that was yesterday, the lava lake was 177 meters, 581 feet deep, with a narrow black ledge around it. Reduced So2 emissions were measured last night. So here's a big change. Some observations. Preliminary analysis of sulfur dioxide emission rates measured yesterday afternoon, December 26th, show that the rates have dropped to about 5,000 tons per day from about 40,000 tons per day, December 21st to 23rd, and about 20,000 tons per day, December 25th. Right, so we went from 40 to 20 to 5. We'll show you guys this in another way here shortly. And what's also been steady since then, that changed that night before. Summit tilt meters recorded continued to record weak inflationary tilt. Seismicity remained elevated but stable, with steady elevated tremor and a few minor earthquakes. And this is something we discussed in our last update as well. Geodetic monitors also indicate that the upper portion of the Upper East Rift Zone contracted while the summit deflated. This was associated with magma withdrawal to feed the summit vents, right? There was no seismic or deformation data to indicate that magma is moving into either of Kīlauea's rift zones. So if anything, the pressure in rift zones has been going down, right? And we'll look at the tilt data later and we'll see that the actual inflation is fairly localized, that not even all the summit instruments are picking up that. So it's really kind of a really localized inflation happening there, probably around that event area. And we'll talk about what that might actually mean as well. So, all right, the west vent continued erupting lava into a lava lake within Halema crater, with 2 narrow channels visible and slightly reduced vigor this morning. So the vigor is something that we're going to keep an eye on as well, right? The vigor has been kind of going mostly down, but then back up a little bit, and back down, and back up a little bit, and we'll show you guys evidence of that as well on the instrumentation. At that point, the lava lake within Halema crater had changed little and was about 177 meters, 581 feet deep. Lake volume remained about 21 million cubic meters, 27 million cubic yards, or 4.8 billion gallons. Right, the lake dimensions from the thermal maps are 790 meters by 520 meters, or 864 by 569 yards, for a total area of 29 hectares, or 72 acres. Right, that's going to our what's become our steady state. We're almost in some quasi-equilibrium now, where the lava level hasn't changed very much. It has gone up and down a little bit, but it's kind of more or less steady compared to before. So, and because it has been going down and kind of draining in, that we talked about how that forms a black ledge as the lava cools on the margins of the crater and of the previous lava level. And so you form that black accretion ring, right, that they're calling here the black ledge. And so that's what they say here. The narrow ledge, which is 10 to 30 meters or 11 to 22 yards ledge around the lake, is about 1 to 2 meters or 1 to 2 yards above the active lake, suggesting the lake surface dropped over the past 2 days. And then we're going to also follow that island that kind of moves around, right? And that's they say here, the island of cooler solidified lava floating in the lake drifted westward, remains stable in size, which is 260 meters by 115 meters, 850 feet by 375 feet. So measurements this morning suggest the island rose 1 to 2 meters, 3 to 7 feet since yesterday afternoon. That's an interesting thing, right? So they're also trying to shoot at that island and see if it's kind of bobbing around, which would be interesting to see how that relates to everything else. That's the kind of information we'll have to wait for a little while for them to release, and so that could be really interesting, right? Because that thing is just essentially floating around in there. Okay, so we're gonna skip the rest of the text. I know it's a lot of text, but Dane, got something to say?
Yeah, you got some questions. Time for some questions.
Maybe I can just finish the update so we can get current, right? So I can talk about what's happening now. And so the update for this morning talks about how the lake was 581 feet deep again, still with a narrow black ledge, reduced So2 emissions. I'll skip down here, 5,500 tons per day, measured yesterday morning, right, on the 27th. So that's kind of above the about 5,000 they said the previous day. So weak inflationary tilt, that's still the same. This portion is the same as the last update I just read to you guys. And essentially the only difference here in observations, 2 or 3 narrow channels, right? Change little as far as the depth, the volume is the same, the dimensions are the same, everything is the same as I just solidified. The island changed just a little bit, and the island essentially was drifting westward, and then measuring about the same there too. This morning, the island began drifting back to the east. So we'll look at that little wiggle the island's doing over there. It's kind of almost caught in a big eddy spinning in that lake, when we'll look at that in a thermal as well. And the island surface was about 6 meters, 20 feet above the lake surface. All right, okay, so that said, let me go back to here and I'll take some questions, Dane, when you're ready.
All right, so the first one is from Michelle Murphy that asks, is the lava pahoehoe or aa?
So that's an interesting question. The lava within this pit now, the surface is very characteristic of pahoehoe, and that's that's just kind of then the fact that it's smooth and ropey and has its plates, right? But that's kind of just one interpretation. Some people might say like, no, actually that's the whole different kind of lava. It's actually a lava lake surface, which is a whole different kind of thing. And of course, if you were to ask Hawaiians, the Hawaiians would say, well, it's actually got to stop erupting and flowing to actually cool and become solid. And then you can call it pahoehoe or aa. At this point, they might call it pele, for example, right? Because it's actually still alive and with circulation of red materials, right, through the cracks there. So, I would generally, to answer your question most directly, it's more like pahoehoe. But some people could get technical and say, well, it's the lava lake surface, and it's not actually the same thing, and all of that. Now, more has to flow out of there for us to have a texture, right? Those are just textures of lava, whereas the chemistry is really identical. So we're just talking about like what shape does it cool and how much gas is it trapping within the cooling rock more than anything else.
All right. Next one is from Kamuela. Do you predict any fountaining in the next 10 days? And what is your expert prediction of the lava chamber underneath it? Is it full?
Right. So, I mean, there is, fountaining is kind of a general kind of term, right? Normally you like to have like some vigor of the lava coming out to really call it fountaining. And so, I've seen some comments from USGS saying that the nature of the eruption now has actually become more what they call strombolian, right? To think of it more like fireworks, more like a poof and a poof and a poof, and like when lava chunks go flying up and then they fall back down around a hole, and that allows the area around a hole to kind of grow taller and taller and taller. That's one way, as opposed to like Fissure 8 was actually just like roaring, and that was clearly a fountain in its own right. Of course, Kīlauea Iki shot into the air 1,900 feet, 580 meters. So that just dwarfs by anything that, Fissure 8 did. So you could go high fountaining, regular fountaining, spattering, and so to kind of put in that context, like is the lava coming out of that hole going to start gushing more? I'll take that as being the actual question and interpret it that way, right? And kind of simplify it for the rest of you guys. That certainly could happen. One of the things we're seeing now is that the volcano is inflating locally under that area of the lava lake, and we think that's because the gas and lava the gas is essentially pushing out with it. It's really like the gas trying to get out of there. That doesn't come out as easily from that western vent as it did from the northern vent, right? And so that's why when that switch happened from the northern vent to the western vent at the same time, we saw a switch to inflation. So that that means that there is some extra pressure building up under there, even if locally, and that could mean that actually maybe can widen that path. Maybe potentially it could find another crack, right? It's tempting as a geologist. Normally talk about eruptions coming up through regular ground, and they kind of crack the rock that's there and push their way through, but they kind of have to force their way through to the surface, right? This area has so many different cracks that there are cracks available that possibly, if the weight shifts a little bit, that maybe that the backflow, and that's an important thing as well. All the lava that's in that pit is cooler, denser lava, right? Heavier, gas poor, and as it drains back down, it's like a big slug that's trying to plug that thing up. And so that's part of the problem there, is that whatever area that's feeding these vents has to accommodate that backflow as well, right? And there are times, and this is also kind of referred to a little bit in some of the USGS comments in the last couple of days. There are times like Kīlauea Iki where we actually saw, like in the lava that came out, that there are different chunks under the microscope. One chunk being from the fresh lava, and one chunk being from the lava that drained back into the hole and got shot back out again. Right, so that can actually happen too. That lava that's getting sucked back in is, interacting with the fresher magma, and then that's changing some of the properties as well. And that might be one of the reasons why the lava is coming out more in this gas strombolian poof, 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 rather than the free-flowing gas. Right, so really, it's about the gas. How easily can the gas come out? And that's really the question there. Can it find a way out to the surface? Is it going to build up enough pressure to kind of push back through that northern vent, or maybe that's just too dense in there now, or is it going to push a wider crack through the western vent, or is it going to push out of another crack through there, or will it push through those cracks in the bottom, which we can't see what's happening underneath the lava lake? So kind of a long answer, but we don't really know.
So this one really plays into that last one, but or your answer there. It's from Ryan Duggar. If the drowned vents were plugged, does the west vent have enough volume to keep the lake heated to remain in a liquid form?
I think there's still a lot of lava going in there. Yeah, so I think so. Yeah, you're basically replacing the cooler, denser lava with that, right? But that said, the whole thing isn't liquid top to bottom, right? I would imagine that the bottom parts you probably already have a shell of lava that's kind of formed. Just like on a surface, we see that black ledge, right? You see the black ledge on the surface. Not so easy to see from the webcam here, but I can maybe pull up an image that has it shortly. You have some margin that's touching what was the colder rock that could have become solid, right? Now, how thick that is, I don't know, right? And of course, if you don't have enough input of lava to put the heat down to that lower part, then that's the balance right there. Like, how much heat are we getting into that bottom part compared to what can be carried away, right? And of course, what gets carried away the fastest is actually up the top and out towards the air, because no matter what you go into the sides, then you basically that kind of insulates a little bit, and it's a slower process there. So I don't know if I answered the last question about the chamber being full, but like, it's at least locally it seems like it's pressurized, and usually that comes from a combination of the magma and the gas. Yeah, and so we are seeing signs of that, at least locally.
Final question for this round. It's about tilt. Matthew Phillips asks, can you explain the inflation on the tilt meter at Escape Road? If you remember looking at that, there's been several microradians worth of change over the little bit longer than the eruption.
Right.
There.
So let's see.
The Escape Road, for those that don't know, is really close to the summit or to the caldera. It's a few miles away, but on the upper east rift zone.
Right. So I am just falling back on what the USGS has said here, that all the signals kind of show the magma evacuating, right? And so
Right.
that is essentially what we expect that the signal actually is. Now, what I imagine is happening here too is it looks like inflation because the blue line is going up. All right, so like this is what I can explain the mechanics of this a little bit more. Right, so the blue line is going up, the green line went up a little bit, but mostly it's on the blue line. So let's focus on the blue line here. If you go to this part of the plot over here on the left, right, where it says raw data, right here, this blue line says raw data 0. 0 is an azimuth, that's a straight true north. So one arm of this thing is measuring true north and one is measuring east. That's the green one, is measuring the east and west tilt, right? So north and south tilt is being measured by blue, and what this is telling you is that we are tilting more to the north, presumably, right? In the direction of 0 is going up. That's what this is actually saying. So that's part one of it. Part two of it, where can I find this? I'm gonna go over here to the Hawaii tracker site, and I'm gonna go to your GPS page here, and we're gonna let this map load here. And we're gonna zoom into it over here. I'm gonna show you guys where this tilt station actually is. And I might zoom in more just so everyone can see. Let me see if I can zoom in more this way too. All right, so drawn on here, this big, looks like a red plus sign, in this station over here to the southeast, that's the Escape Road station. That's about the area that it's in. Yeah, so what it's saying is that at this location, the ground is tilting that way, right? More. So that could happen. The rift zone in this direction is, so this is our caldera up here. This is the summit caldera of the volcano. The inner pit of Halema is this one right in here. All right, so we have other instruments that are closer by. like this one on the south and Wikahuna on the north, right, that we often refer to as well. So the one that's showing inflation currently is this one, whereas the ones, there's actually one over here as well, somewhere by Kīlauea. And that one is showing deflation still too. Right, so it could be that we're just seeing a sag, right? If the whole caldera, there's actually another caldera line that kind of what we call the Great Caldera, that has a greater arc that goes around something like this. Right, that's the farthest cracks formed by the volcano during collapse. So that's something more like that size. So it could be that if the magma is, draining in the direction where it's deflating, then this thing could tilt to the north, right? That's one way that could happen. Of course, if magma were to inject into the rift zone as well, you might also expect it to tilt to the north. So this is a station that's a little bit ambiguous and has always been so, and it's always been a little bit tricky to interpret because it is in that more or less meeting zone between the Upper East Rift Zone that's right through here and that Summit Caldera, right? Because, right here is that Great Caldera, here is our main caldera, right? But here's Pauahi Crater. There's actually a cliff over here if you're going in this direction, right? So this is a clear feature that's recognized by geologists everywhere. So maybe that answered the question. All right, so
Yeah, I think so.
we'll go back and we'll come back to the tilt a little bit more in the future. The USGS does have a monitoring page as well, but they don't have these azimuths that Dane actually put together here on our Y tracker page. So that's where you can kind of see that kind of detail if you don't visualize it better than just looking at the numbers on that graph. All right, so I wanted to show you guys the trend of the SO2, right? Because the reason being is that without going into all the scientific background of it now, but SO2 emission rates are tied to effusion rates, right? The amount of lava coming out is proportional to the amount of gas coming out, right? So because often it's the gases that's bringing the lava up to the surface, right? Essentially that's the buoyancy that's required to bring the lava up. And then the more gas there is, the quicker it can bring it up. It's kind of as simple as that. And so we've discussed, so I kind of wanted to point out here, before the eruption, we were kind of at a background level of around 50 tons a day coming out of the summit through that water lake that groundwater was kind of absorbing and buffering. So I don't know, the measurement could be somewhere else in here. It's kind of hard to tell, but no matter what, it wasn't something like 40,000, which is the number that we're reporting from the 21st to the 23rd by the USGS, right? So that's, these blue dots are the actual USGS data right here. That one, that one, that one, that one. I didn't catch a measurement for the 24th. They said 20,000 on the 25th, then they said 5,000 and 5,500, right? So I just put in just a regular kind of fit in here, just to kind of visualize a little bit what a typical eruption rate might actually be like, right? And so we kind of pointed out in the past updates how depending on how fast the eruption is coming out, you can have that kind of shape. It actually can go up and back down like that, or it could go up and back down and tail off for quite a while afterwards, or it could go up and just come crashing down and be over, right? But that typically, the higher the peak of this, right, the higher the eruption rate overall, the faster the crash, right? So it's interesting to see that we have seen our 40,000 high, we've seen our 20,000 middle, we've seen our 5,000, but it hasn't gone down that second day. It's actually seems to be adding a little bit of a tail, at least so far, right? So that's kind of why we put this together here. So this part right in here is the question, how is this going to develop over the next few days? It seems like we've clearly passed our high here, right? But we also have seen on the tilt meter, and maybe we just jump to the tilt now from the USGS. And this is a summit tilt in the past 2 days. So here at Wikahuna, it's basically rising. The ground is swelling. And this is a change from what was happening previous to 26th, as we see in the past week plot, right? And kind of zooming out further the past month, you can kind of see here, that's just this last little bit of the plot after that large drop that kind of characterized the beginning of the eruption right in there. So that's a tilt I've mentioned before. We just looked at the escape road. Let me go back up here and show you guys the Kīlauea station right in here. Kīlauea maybe had a little bit, but the trend generally is downward still. Right, so Kīlauea over in the east is not showing that inflation that far. So the inflation is localized, right, to Uikahuna, right, the station in the north where we do see it there. And I'm not seeing the Sandhill station reporting a graph at this point, and nothing from our summer camp station in the last day as well that we can rely on. So that's a little bit of our tilt signal, and that's kind of just showing where the ground might be swelling, right? And so to kind of come back to this, maybe since we have inflation, we could sustain a longer tail here, but that's really the big remaining question, right? We're certainly past this part, it seems like. You'll be surprised to see the gas emissions go back up to this level at this point again. That would be a big surprise. And if that were to happen, that would mean there's some fresh batch of magma that's come up and brought a whole bunch of new gas, because the current batch, you'd imagine, has already bled out most of the gas to this point already, right? If you think about like how much space is underneath this curve right here, right? If we're down in this part over here, we're only adding a little bit total to like the bulk of it's been emitted already in this eruption. All right, so that's kind of the trend to date, and let's review some of the images here. Let's go back to the 27th of December and show you guys this one where they basically toggled between December 25th and December 27th, right? And kind of see that the big change there is that on the 25th we still had that northern vent erupting. Maybe I should zoom this in. I'll zoom this in for you guys here. On the 25th, we still had a northern vent erupting, and the lava lake seems a little bit fuller, kind of lapping up all the way to the edge over here. Yeah. 27th, 25th. Right, 25th. The north vent is shut off, no gas, no glow, no nothing, just drain back. Our west vent is glowing now, and the lake margin is a little bit lower over here. All right, and here's our ledge that's formed right in there. And I'll go back and forth one more time so you guys can see. All right, so that's the first image was released yesterday. Kind of zooming in here. You can see there's our western vents, and we actually had a third spot right over here that was putting lava down in our last update right in there. So that one seems to have shut off. We still have a trickle in this one. Our later images are going to show that this thing actually crusts over and forms a little tube right in here. That gets covered up, and this thing is the one that's got the big open channel still, right? But at this point in time, you see there's nothing happening over here. We don't even see any kind of drain back, like really obviously happening right in there. Right? It's interesting how that's happening right in there, but it could be happening there. It could be happening in that lower middle vent that's right in here. It had a lower spot down lower, and then there's a lower spot underneath here as well. So of all of those areas, essentially only one of those cracks is still putting out lava that we know of, without knowing what's happening at these other two under here. So zooming back in here. So here's a view. I'm going to scroll down and see their caption. So there's a 27th. You can kind of see there's that third location talking about the glowing hole that I just pointed out to you guys right there. You guys can see where this thing is plunging in. Right, this is like the start of that whole circulation of lava that's coming out in that direction. Right, and you kind of see a little bit. There's like little bits of lava through here that might be coming through little tubes, little buried areas, and this thing is already getting pretty narrow right in there. And you'll see it's going to zip up, right, just like that analogy we used yesterday of rivers in the wintertime forming ice in their banks. They meet in the middle, and then the water still flows underneath. The difference in Hawaii being, with lava, that there's no spring thaw, right? It just kind of stays closed off ever more after that. So another view here, scientists measuring on the south rim, looking down into this pit, right? Here's our tripods. Mauna Loa here in the background with a cloud bank on top, if you're wondering. It's kind of hard to see unless you zoom in, but that's what's going on there. And a view here showing decreased vigor in that western vent, right? So now in this image, we see the open channel on this side, but we don't see so much red right in here. It's kind of covered up. Let's see if I can get that to look a little less blurry for you guys here. Or maybe if I click on on that one. Yeah, that's I think what we get. So there goes all the gas coming out of there, right through there. You see a little spot of lava right in there, a little bit right in here, and so it's kind of still flowing from here to here. It's just zipped up underneath that lava crust now. And this one has not formed a lava crust, right? So if this thing was actually putting out a huge amount of lava, then it's harder to form a crust because the actual moving lava keeps it open. So this particular hole seems to be putting out less lava, and that's part of the decreased vigor that they're talking about there. So let me back up here. And here they have a nice comparison image from the 26th to the 27th of what this actually looks like, right? So here are 26. That very, very western vent is active, right? There's a little bit of crust over happening right in there. You see a nice little delta pattern happening here in this steep line, but there you have a plunge pool right there, several plunge points. The middle one you can see is still pretty vigorous, right? Like there's no way you can form a crust if you have that much turbulence on the surface of your river or your cascade of lava. So all this like kind of darker material through here, that's all crust forming, but it's just getting carried down and dropped into the lake at this point in time. And over here is kind of easternmost one of those. See, it has a little bit of a crust forming on it, kind of bubbling up. Of course, that's not something we see anymore, so that must have gotten pushed out of the way by the vigor of this particular fountain, right? That's something we've discussed happened before as well, right? It's typical for Hawaiian eruptions to kind of, and this is kind of the small scale pattern of it, but in the grand scheme of things, when you form a crack through the ground, the crack isn't perfectly even parallel the whole length. You're going to have some areas that are wider and some areas that are narrower, and it's going to be kind of jagged. And so the places where the ground is the widest would be where it wants to come out the most easily. And the places where it's the narrowest, those eventually seem to kind of seal up. And then you focus eruption on areas that are kind of wider, and that kind of allows the bulk of the lava come out of one spot rather than kind of staying spread out for a long period of time. So, we saw that in 2018, the whole pattern eruption, we saw that Kīlauea, and it could be that on a small scale we're seeing that here, where essentially we're focusing to this one vent over here on the right, because you can kind of see here in this right photograph, right, we don't see that chunk still in place right there anymore, right? So maybe it's was able to push its way, although the margins over here do seem higher on the banks. You don't see quite as big an opening as we did on the 26th. So maybe that also speaks to a bit of the lowered vigor that they describe here. So, all right, this is all the USGS page, and here is a HVO scientist making observations, looking down into the pit there, right? There's that little area we're just zoomed in on right in there. So that was the 27th. I want to make sure I cover the 28th, and maybe I can take some more questions after that. After we kind of review our most up-to-date imagery here. And so there is the lava lake. This is that western vent, and you can kind of see it's starting to become visible above this rim of the crater right in there, right? This thing has actually been building up. I described how it's putting out lava and spattering. That lava is kind of falling around itself. There's a report in one of the comments that the cone is what was it, 100 and I forget, I might need some help here, Dane. How many feet that thing was above the lake surface? 141 maybe?
131.
131.
Yeah,
so,
up 20 feet from the previous day, I believe. Right.
So it was at 111 feet above the lava level, and then now it's at 131. So that is indicating to us that the actual rim around the vent has actually gathered material and it's built up 20 feet. 20 feet is, a lot on human scale, but that's kind of a small one for the volcano. We saw, how, I don't know, maybe once again, Dane, how tall are some of those hills down in Leilani and Lani Puna.
Right. If I remember right, Fisher 8 last measurement was 180 feet, just for comparison. And it's, features like Green Mountain and Haleakamaina. Those would be, even if you don't take in the compression over hundreds of years, right? They're still much bigger, more predominant features.
Right on. So there you go, a nice comparison. Fisher 8, which is just down a street from where Dane is, answering your guys' questions right now. So, okay. Also interesting to see in this particular video image right here, it looks like you have some bubbling points coming up through the surface of the lake, right? Kind of that would indicate that there's some gas coming into this from below, right? A lot of the gas is not able to escape as easily. Maybe if it's going through that little lava tube, it's a little bit more gas rich, and that's something that could certainly help keep the lake liquid longer and keep it circulating longer, right? Because that essentially reduces the density of that lava, and that makes it kind of more fluid, and there you go, that allows it to circulate. So not as obvious from this really dark image that this is the island there in the middle, but that's what we're looking at there. That's the island that's sticking up at the middle of the lake. So here's a view today. You can see that western vent looking very similar to how it did the previous day. So there it is, the trickle coming down. You see I don't know if it's worth zooming in more. I don't know if I can. But there's a little glow spot. So the lava is still coming out of here. It's just doing it underground and plunging into the lake right in there. So it does have a path in there as well. There's a little bit more over here. And you can kind of see, look at this hill that's growing up here, right? And that's probably from the times when it's really burping out a lot of gas. Maybe the gas is coming through like, more like a bigger burst and then like a little bit less, and then a bigger burst and a little bit less, as the kind of bubbles can collect and kind of start putting pulses of emissions out, right? So maybe during those higher times, if that's happening, you might have more accumulation of stuff here on the sides. All right, so we'll keep going and see what else we can see. We don't really see a whole lot of evidence so much here of this northern vent really being a player. Although the fact that the lava level hasn't been rising is our biggest indication it's going to be draining back in somewhere. Right, if not here, then one of those other buried vents. Okay, I'm Matt Patrick with those photographs yesterday morning, December 27th. There's an image of sunrise. You can kind of see that where these guys are positioned. The old crater and drive used to go all the way around to Kīlauea crater, and here's the line of that road right there. So this is where the road collapsed into the pit. On one side, and there used to be a road, and then connected back, and there's a spot over there somewhere that has the other side of the road kind of hanging off. So they're kind of looking, you can see this is east, crater is that way, they're looking more or less from the south into the pit. And nice rainbow image here, and image of their very, very fancy laser rangefinder, right? That's shooting down with 1 meter accuracy to see the surface of the lava lake changing, to see the surface of the vent changing, to see the height of that island changing within that pit as well. Right, so that was a little earlier. Let me give it a reload to see if anything else shows up here at the bottom, since I started loading my page here for you guys. And the video I showed you guys earlier is now up as well. And we also have an aerial photograph here. Yeah, that's the one we just looked at. All right, so we're going to do the thermal images next, but let me see what questions we have here lined up for us, Dane.
Right, so we have a few here. Jonathan asks, what is happening just below and for 500 feet under the lava lake crust? Can you create an image of the likely activity, including the source of the eruptions? So I think he's kind of talking about the dynamics with the vents coming up from depth, and then the pooling lake there, and then potentially, it draining back into the vents, and just kind of how that system might work. This might be a good time for the John Madden pin in Microsoft Paint or something along those lines. But I'll let you take that one.
Yeah, that's for just below for that. So then the crust it's really hard to answer that without some more illustration like Dane is saying, right? We do have some old diagrams, and maybe what I'll do is for our next update, I'll bust out some of the old Jagger diagrams when I do have some of those cross sections and how they imagine those pits actually are. We can compare them to what we might have happening here, right? And of course, the big question for us is whether the flow is out or into of those submerged cracks, but we know they're there, so we definitely could draw them in some kind of schematic cross section for you guys. So yeah, I will take that as homework, and punt on that one to the next time, because it's hard to really say, right? Kind of a quick take at it. If we were to kind of draw like a bowl underneath this thermal image right here, lava is coming in this direction, so on the surface it's going this way and this way around, right? But at some point it's got to plunge down and in, right? And that's happening continuously. So it's going down and in, and then it might come around and come up. I'm not sure exactly, but there's some dynamic, something like that, of the overall grand circulation of it. That's just with one input source of just that. Then you're going to start perturbing that with a drown vent over here, and a drain possibly over here, and a drain possibly over here. And we will look at the time-lapse image of the thermal shortly here to kind of show you guys whether there is draining actually happening in there. So in this particular time frame, right, with 1 image per hour with an automatic USGS webcam, it's not so easy to tell that there's any draining happening in the last 24 hours here, right? It's not no obvious flow all going into here, right? I don't see, it's hard to tell if there's any flow going that direction right there or not, right? Whereas clearly it's going this way, and clearly it's going this way, right, from the source. So that's what I'll do for now, and then I'll try to do a better diagram and bring up some of the historical analysis of that. So thanks for that question, Jonathan.
All right, so the next one is this one's from YouTube. If the flow stopped today, how long would it take for the lake to solidify? Assuming that another eruption doesn't circumvent that.
Man, so that's a good question. I'll refer back to the Kīlauea eruption happened in 1959. In 1959, once the lava stopped going into the lava lake actually kept turning over, like because it would form a crust, and then the heat and gases would accumulate below, and then that would essentially erupt through the crust, and that allowed the crust, which is now the coldest, heaviest thing, to sink back in, almost like a conveyor belt coming in, and be replaced by red lava. And so the whole crust would turn over from black to red, and a few minutes later, the whole thing would harden all the way back over and solidify again. That happened for something like 9 days after the eruption was over in Kīlauea. So once lava stops coming out of the vent here, we're going to still be able to watch this thermal image and see that process happening that we weren't able to catch at Kīlauea. That's going to be awesome when that actually does happen. But that's kind of part one of it, so that, to actually form the crust over the top, this lake is deeper than Kīlauea. It might take a full 2 weeks or longer for this thing to form a hardened crust where it's no longer then moving around, right? And then you might just see cracks at that point that are hot and putting out gas from the cracks, where the lava lake, as it's cooling and contracting, is going to pull apart and allow those vents to kind of come up. And you might have small little spatter things coming out possibly too, and that's something that we've seen in the pictures before, right? Little cones that are called hornitos, like over top of these hardened lava lake surfaces, and all putting out spatter of lava and gas. That's something that could happen as well, But to finish the answer, Kīlauea, 440 feet thick, we believe got all the way solid in about 36 years, something like that. So I want to say, like 1988, somewhere in that range. No, 1995. I think it might have been actually all the way solidified. And of course, solid for lava is somewhere around, what they were measuring. I think I want to say, I have to look back at the graph now, but somewhere in a range of 1100 Celsius or 900 Celsius, like that kind of ballpark. So solid doesn't mean cold. That means hot. I mean, hot but solid. And so solidify was a question. Kīlauea is still hot today, more than 60 years later. Still steaming.
This one comes, I've seen several questions kind of similar to it, asking about samples. Have they dated the lava coming out of this eruption like they did the 2018 eruption, kind of like the 1955 beginning phase of the 2018 eruption, where we had a residual brought to the surface that was stored in the rift?
Right. So I don't know is a straight answer. I can only know what that they haven't released anything that we've seen publicly about that data. So I don't believe.
Right. I will say that the way that they were sampling the water lake was with a drone, and just looking at this lava lake and the way you would have to approach it, which would be basically straight down into it. Yeah, the drone ain't going to do too well on that one. It's possible, maybe, but it's going to be a logistical challenge compared to the water lake.
Right. And let me add that, this eruption is not like 2018 because, people's lives are not at risk. And, that was done in 2018 because it was much more of an urgent thing to know how the thing was going to erupt in the middle of the neighborhood. That mattered to people's lives, right? Like, whereas in here, it's more of a scientific curiosity. So I can see them, okay, we're not going to risk the drone because we really don't really need to know right now. We can,
Right.
after the thing's all the way done and cooled, whenever that happens to be, then we can send a drone down there with a little, or, equivalent of the Mars rover or what have you, some version of something like that to go and scoop up some of that lava down there, from the island, from the lake, what have you. They could even rig something else up that's, more ingenious or high tech than that.
Right. All right. So I think we got one more question for this round. Yes, this one's from YouTube as well. What's the chance that lava will find its way down to the fissures from 2018? Since we're talking 2018 already.
All right. Well, so 2018, the fissures themselves, Leilani Puna, those fissures themselves kind of shallow. I think that there's a very low chance of that actually happening, right? Because that's where the lava drain. Same thing as here. You have that kind of drain back of lava in that area. Those areas where they're more shallow, they're kind of they almost heal and form like a scar tissue, right? It's rare to see lava come out of the same fissure more than one time. It might come out of a new crack 5 feet to the side, but rarely will it come out that same crack it came out of a second time, right? Almost, because it does form that kind of scar tissue, as I think of it, right? That the lava that goes back in the hole is gas poorer and it's more solid and it's harder to crack than a lava that has gas in it, because when you're cracking a rock, what you're really doing is going to crack between one bubble that exists and another bubble that exists. You're just going to crack that little gap. You don't have to crack through the solid rock the whole way. That kind of reduces how much strength it takes to break the rock, as you might imagine. So rock with bubbles in it breaks with more bubbles and bigger bubbles breaks easier than rock without bubbles in it. This might be intuitive. So very rarely do you get it coming out of the very exact same crack. Now that said, there are other areas where the ground certainly is weaker, right? The ground we know is weak around Pu'o'o. We know the ground is weak around Makapui, right, where all that lava drained out of there before. We've seen eruptions in that area, back Father's Day 2007. Like, that's an area that's been erupting during Pu'o'o. Napau also erupted during Pu'o'o. Kamomoa erupted during Pu'omoa. That, mostly that kind of upper part of the Middle East rift zone from Manaulu is one of the weaker areas, right? And then progressively down a rift, there is a chance it goes a little bit further. We've seen eruptions in the past that might have gone as far down as a Jonica station, like in a forest reserve, for like a day eruption, put out one pad of lava, the ground moves a bunch, right? And I think the bigger hazard in areas like 2018 eruption area are more the ground settling and moving and adjusting from the pressure of things rather than lava coming out of there. Because it is, a rift zone is a combination of a magma pathway and a fault zone, right? So it's still a fault zone. It can still move. The ground can still move and settle. And that may be a bigger risk, that the ground might settle in some way rather than lava coming out of it, right? That's kind of, my personal take on that. If lava were to start going down Upper East Rift, because people want to know about this, maybe it's worth talking about in a little more detail, right? It has a lot of work to actually get all the way down there, right? Normally. Right, I'll talk about the general pattern and I'll talk about the exception, right? The general pattern is that, you have an eruption that happens at Manaulu. Then you have one that might happen just down a rift at what used to be a Lai crater, now Makapui crater now, or Kananuyohamo. Then you might have an eruption that's at Napau or Pu'o'o or Kamomoa. And then you might have one that's a little further down at Jonica. And then only after you kind of go through all those steps can you get to somewhere like maybe Ala'ili might be the place the ground seems the weakest based on the post-eruption, right? It seems like there's magma underground there still, whereas you don't see that same pattern in Leilani. That's why I think Leilani is kind of the scar tissue area, whereas a little further back in Ala'ili might have more areas for long-term concern, because we've seen magma collecting underground over there, right? Now, the other part of this whole process is that eruptions in the lower East Rift Zone and East Rift Zone in general are balanced between magma coming into that fracture and the south flanks to the side, allowing it to pressurize, right? If magma comes in, our south flank just says, "Oh, more magma. Excuse me," gets out of the way, and more comes in, just moves out of the way. Then it can never pressurize or even erupt. It's just going to be filling the space passively. There's going to be magma going through there. There might be sulfur emissions, there might be ground movements, that kind of thing. But you may not actually have lava coming out of the ground either, right? So we know the south flank is still moving, and that also lowers the chances of pressurization of magma down the rift zone at this point in time. So there's a lot of different parts to the answer there. Right now, someday that's going to happen. The exception had to do with like eruption of Kīlauea. Kīlauea First, what happened was, Kīlauea happened over the course of a month at the summit, and then over 2 weeks, the magma migrated downrift all the way to Kapoho, and then erupted in Kapoho for another month down there, all the way essentially at the shoreline almost, going into the ocean, of course. But the reason that was different was that was tracked by a series of very deep earthquakes that brought very deep, fresh, hot magma up to the surface all at one go, and that lava then was stuck inside of the crater and drained back. I think it had a combination of that really hot magma and that really dense stuff coming back in, and so the dynamics were very different then. We didn't have a big collapse crater in a caldera. We had essentially had a very full cap over the summit that was allowing all that pressure to be held in and kind of transfer to Kīlauea, to the point where the fountains of lava at Kīlauea were 1,900 feet high, right? We didn't see anything like this eruption, so we don't have anywhere near that kind of gas pressure, magma pressure they're dealing with now. And therefore, there's also a lower chance of that extreme case of magma going all the way down the rift happening as well, right? So I kind of, elaborated a lot on that one, but I know a lot of our viewers, especially in Lower Puna, have that on their minds, right? Of course, it is a balance of how you live in a rift zone, right? There are other things to consider besides volcanic risk. There's always volcanic risk in rift zones. That's never going to change. It's only a matter of when, not if it's going to happen, right? So long as we're okay with that, and other benefits of being in the area, the culture and the quality of life and everything else is worthwhile, then more power to you, right? So next question, Dane? Or is that it for now?
Yeah, we can call that good for now. We'll get the last batch up for you at the end.
All right. So I'm having this thermal image here playing for you guys. You guys maybe have noticed, you guys have been staring at this this island right in here, right? How it's moving, right? And so it's kind of doing this little circle dance, going up and over and then almost back down, right? It's almost like it's caught in an eddy, almost like the lake is circulating like this, right? Something like that. We'll have to kind of analyze it a little bit finer resolution to tell that, right? But the other thing you can tell in this image right here is that we now have on a bottom part, the western vents more clearly visible. You can actually see this one stream and another stream and another stream right in here in the thermal images, and something happening here a little bit lower down as well, right? So there's actually quite a lot. It seems like it's pouring in right in there based on the thermal pattern, right? This is the one, like a place where most of the heat's coming in is right down in there, right? And so here we can see our black ledge over here. You can see how the lava is pulsing on it and then off it, right? Maybe something that's been obvious here as I've let this thing kind of loop for you guys as you watch, right? So the lava level was rising and falling and rising and falling, and so I'm going to go out of the order I prepared it, but I'm going to jump here to our seismographs and just show you real quick in our seismographs how we have areas of darker ink and then lighter ink and then darker ink and then lighter ink, right? The tremor is variable at the vents, right? Normally what this is actually measuring is vibration of the fluids, the gas and lava coming through the crack underground and then out at the actual hole that is coming out as well. Right, so the whole thing vibrates. And we'll skip that unreliable station. Here you can kind of see this one right there. There's our dark blue, another band of dark blue, a little bit in here. And I think one of our better stations are coming up. You can see that one there. More of the same pattern, Here's our Byron's Ledge station. That was kind of one of our more telling stations. Showing one clear band, clear gap, and another clear band of activity, and then more gap. You can see a little bit more of something happening in here, right? This could be actually magma still, they're just trying to figure out which way it's going to go. There's magma draining in there that's cold, that's colder because it's degassed and put heat out to the atmosphere, and lots of gas as well going back in there trying to get past, and the lava that's coming out is trying to get past that as well. So depending on I have no idea what shape and size the actual connection is to the magma that it's feeding it is, but that's where that dynamic takes place, is down in there. So okay, let's go back to our thermal, which is here. All right, so I also want to point out those other little islands, right? So there's one. All those ones were here, right? And one of our last update, we saw that when these things first started moving away from this northern vent, they were actually moving in pair, this one and this one, like they were connected. But clearly they're not. They're now diverging now, kind of all drifting their separate ways now that the circulation has improved a bit in there. All right, so let me just, what I'm going to do now is I'm going to switch over to this other more high-res version of the time lapse, and we're going to start back when the lava level is still lower. So here's a northern vent. You can kind of see it's clearly plunging in. At that point, the circulation is coming from here around this island in this direction, right? And so I'm going to play it, and then we'll pause and show you guys. You guys can see the island is starting to move to the east as that northern vent activates. Right, you can kind of see clear on a positive. You can kind of see a clear pattern of circulation going this way and this way out of this vent, right? And so you can imagine that they come together somewhere right in here and go down here, and then back this way, down and back this way, right? And that might be what's actually pushing the base, the rudder of this island, so it's actually being pushed towards that vent right in there. Yeah, so rewind it a little bit so you guys can see there. Circulation, right? So let me play it a little more. You can kind of see the lava is kind of rising and laps up on the edges, and it's rising, rising, rising. And then something changed right there. So let me pause it and let me. Yeah, so this is our western vent taking over circulation now through here. So, but what I wanted to do is rewind it a little more to where a switchover actually happens. All right, so our northern vent's still active. And we're going to try to watch for circulation. The island is certainly going to move this way, but like what we're going to look at it is lava draining back into this pit from these directions. Does it switch from coming out to going in that spot? So let's play it again right in there. So right in here, in this part of the video, the lava appears to be draining back in. You definitely see some movement, like some backflow at that early stage happening at that point in time, right? Now, if we go a little more, still looks like it's actually going in. And then by this point in time, no longer, right? So let me pause it right there and try to zoom in. Oh no, it doesn't let me zoom in. All right, so what I want to point out is this pinkish zone right in here looks like a little bit of a crust forming right then over top of that vent right in there. It doesn't last that long, but if you have a crust or like a little ledge forming right there, then lava really can't be draining back in, right? So it seems like it stopped a little bit right in there. There it kind of breaks open that crust. And it's not really clear there if the lava is flowing in as much as it is going past there, right? It seems like there's certainly a little bit of component of both in there. So that's an interesting thing to look at there, and you know, something I'm looking for in a circulation of the island as well. All right, so I'm looking at now. There's this little piece of rock, this chunk of rock right in here. You know, if the flow is going past it that direction, you can kind of expect it to have like a little bit of a cool spot behind it, because the lava has to split and go around that rock on both sides, right? It's kind of a small thing, and I wish I could zoom it in a little bit more for you guys here, but let me play it and if you guys see. Pull it all the way through for you guys one more time. And I'll pause it when we get to the western vent again. Right? Maybe you guys saw, clearly there was a flow going in, and now the flow seems to be going around over here by this point in time. So now I want to point out to you guys is the vents down here. So let's keep an eye on the vents on this lower part of the image right here. So you can kind of just barely see a little bit of the glow where it's coming out. You don't really see a whole lot of structure in here because the vents are kind of far down at this point in time still. But as our animation progresses here, there's a point in time where we see that pulse, like right in here, those fountains are getting bigger. And look, by now, we now have some cones that we can now visibly see built up where the lava's coming out of right in there, right? We'll go forward a little more, and back a little more. Forward, and back. So there's that extra 20 feet between 111 feet down and 131 feet down. Right, that you can kind of see that could be 20 feet building right there, just from the actual spatter during that kind of one pulse of it, right? At which point, lava is also spilling over onto the ledge, right? And the whole surface is much hotter. Well, we have to compare the actual numbers off the screen over here, but but you can kind of see this. The circulation seems to be going more because the amount of crust and the heat of them seems to be more broken up than in the previous frames. Yeah, so that's a fascinating thing right there, right? So you can kind of see the things lapping up onto the ledge there, right? And you could actually have some little structures in here. I saw there's one frame on the kind of current image where it looks like there might be like a little bit of a lip right in here, and the lava kind of spills over, and it makes like a little puddle for like a frame right in there. So there's some kind of other little weird things that can happen in this little ledge area as well. So, all right. We will move on from the thermal analysis there. And we will show you guys that the USGS, let me refresh this here. USGS has been putting out some new maps on our maps page. So let's go back to, what was the last one we saw? 25th, I believe. So let's go back to this one on the 26th and show you guys some of this. Let me zoom in here. We can kind of do these one at a time. So this is essentially their new DEM that they've made by doing a scan. So they have the elevation of the lake surface. You can kind of see the islands in there. You can kind of see the rafted island right in there. And they can then get an elevation based on a DEM that they actually have right here, right? So that's something that's interesting. Showing the west vent. This one I thought was also interesting. This one's kind of tracking the position of that island raft. So green is where it started off on the 21st. On the 22nd, it had got over here. On the 22nd, it got over here. The 23rd, it got over here. The 26th, it was over here. And now we know that on the 28th, it's actually back over here again. Right, the thing's kind of been bobbing around. So I'll find some of those old sketches that Jagger and his colleagues put together. So another map here showing lava lake depth and kind of showing different lava levels at different points in time. My different contours here on a map. So that line is 21st. That's the 22nd. That's the 23rd in red. And the highest one there is the 26th. That kind of maximum point. Maybe not quite the maximum point right in there. And they also have an image that goes along with it, so that it can be a coherent story for everyone who's looking at just that one composite right there. So that's the first map. Let me click back here and show you guys that they have also put out a contour map. Quite similar to what we covered for you guys. You guys have been following us for a few days. We did exactly this, I don't know, 4 days ago now. Put out a contour map that emphasized the 800 meter contour. We also did an 850 and a 900 meter contour right through here, right? So to kind of estimate how long it would take to spill over into this one little patch right in here, if it kept at that same rate of filling as it had in that initial part of the eruption, which it hasn't, obviously. So now we'll be lucky to have this thing rise any more than here by the looks of it right now. So that's interesting to compare. So I'm just going to point that out. And let's go look at the thermal map. So they're also doing thermal scans from those helicopter overflights, like the video we showed you guys coming in. And that kind of allows them to do a composite over top of the aerial imagery, showing all the different crusts, the island, pieces of island over here, and heat of the vents, lack of heat. You have the northern vent right over there as well. So yeah, if you guys want to look at it more closely, you can go check the USGS site. This one was one that might have been the most intriguing to me personally. They also summarize, of course, 73 acres, 29.6 hectares, active lake depth 176 meters, 577 feet, and volume 5.6 billion gallons, they're now saying in this particular graphic. And so we actually haven't shown in red here. That's the actual extent of the lava lake, right? The kind of a little bit more peach color, pinkish color here on the edge. That's the black ledge that's on the side. The orange right here is the vent. It's active. The north vents is dark red. In yellow, they have the islands right in there. They have in black dash line right in here the trace of the 2008 to 18 lava lake, right, which we've been reporting for a while, is more or less the size of the former water lake and of this island complex right in here. So kind of interesting to compare the size of the island complex in position not that far out, floating above where that old water used to be, floating not that far north of where much higher elevation than this, there was a big chimney of lava that was spilling over lava lake in 2018 and spilled over something like 70 acres as well with its flow. Although it was much thinner, of course, it wasn't all quite so deep, right? Almost 600 feet deep in the middle. All right, so the maps are interesting. There's one more here that's showing topographic changes, right? Kind of just emphasizing that they had taken a DM in 2019 that still showed this downdrop block and didn't really have any water in it yet. And then now we can kind of redraw the surface as it looks at this moment in time, or at that moment in time, since it's certainly changed since then. This island we know has actually moved, right? So, and they also have two cross sections right in here. So you can see down here at the bottom, the cross section, Halema rim, that's this edge right here. Caldera rim is this edge right over here, and this is a higher one, right? And the water was way down here. Islands right in there. So they actually have it on topography. That's based on their scans and surveys. So fascinating there. So I believe that are all maps. That's the same one again there. And so we want to make sure we also go and check USGS Twitter to see if they have any more recent updates coming through here. And so let me look and show you guys they've actually updated. Now they got a picture of that western vent as their profile up there. And we have their video. We have their summary, 72 acres, 581 feet deep. However, they actually had earlier reported that on a caption of one of their images that the lake was not 581 feet deep. It was actually shallower. It actually had possibly drained down since then. And so Dane has actually asked the question regarding 581 versus 558 at 4:30 a.m. today was the caption of the image as well. And so USGS has responded, and here's just like a little bit of a peek behind the curtain as well. Some different reference points were used, resulting in variations. Oh no, I clicked on it. Using the same reference point as of 10 p.m. yesterday, lava lake was 177 meters, 581 feet, and today it was 2 meters deeper, 586, 5 feet deeper, right? So Essentially, don't listen to that caption because it was taken using a different reference point. And by the calibration, to be consistent with what we've been saying, we're going to use this number right here as that more current depth of what's happening at the lava lake. All right, so that is the that imagery we have. I want to make sure we cover the biggest impact of the eruption so far has actually been the gas, so we kind of want to make sure that we definitely cover the gas. And here we have our air quality data coming up, showing a yellow for Kona. Right, and we've kind of covered this before, so without going into too much detail of how this works, we're just kind of show you guys a history, and Kona itself has been in the yellow or near the yellow for most of the day right there. Right, one of our Kona residents pointed out to us that you can also look at this on Purple Air, which for some reason is not showing itself. Okay, here we go. Purple Air also has a website, with user data submitted here, so this might give you a better indication. Excuse me, sympathizing with that bad air over there. All right, but showing a little more how we have readings in orange: South Kona, Kīlauea Kona area, North Kona, Manalani Resort, Waikoloa, Waimea. Right, all those areas are showing impacts of the gas. Excuse me. So let's reload to make sure we have the latest VOG model here from University of Hawaii. We can kind of see here that we have a big impact, especially in the reds in the areas around Pahala and Ocean View. Nalehu is a little bit out of it, down closer to sea level, but you can kind of see this big cloud is stuck around all of Kona, right? And so let's go back and look a little bit more zoomed into our island map. You can kind of see that the wind can bring in, let me change my color here. The wind can bring in the gas up to the Waikoloa and to the Waimea areas right through there. But then probably the trade winds coming over the top, when they come in, they probably keep it more on that side. So Honoka is still showing good air. Oh, excuse me. All right, we'll move on. So let's check the park monitors. Here we are in a park. Park has been showing green most of the day, with one small spike of kahuku down in here. So viewing conditions for those coming to see the glow tonight are looking good. We want to look at the windy distribution kind of worldwide, and the way that the winds have lined up. Here we are in Hawaii, way over here, and there seems to be this channel that can direct some of our bad gas. It was going to California yesterday, but now it's a little bit going across Baja, but it actually may be getting swept across as part of all that other stuff going there. Of course, there's Mexico City in there as well, so from this point on, it's hard to really tell what's going on, but certainly a big impact. And if we zoom in on Hawaii over here, you can see that quite a lot of red right in there. So that's the So2 from the satellite. And speaking of the airspace, I wanted just to point out here that our current airspace restriction is set to expire tonight, right before midnight. And so I would not be surprised if we have a new announcement come out here. Oh, in fact, it was just issued to extend our air restrictions until January 4th, midnight. And it's the same thing, 3 nautical miles, up to including 9,000 feet. All right, so you can go above that. You can go above it if you're 9,000 feet or higher. You can go closer. You can go lower than that if you're miles off to the side. Right, so that's the status on air restrictions right in there. All right, so we talked about the tilt a little bit here. And, the interesting thing is that the tilt is still rising, right? And that's kind of the question is like, can eruption really wind down that easily with a tilt still backing up like this? Or does this mean it still has kind of some backed up pressure to vent off before this thing can kind of wind down and kind of extend it longer than maybe we had expected, right? We did have an eruption in 1934 that lasted 33 days at the summit in a very similar pattern as this, so, that could also be in play. An eruption that's a month long, possibly even longer, right? But I wouldn't bet on it personally, if I was a bookie, I wouldn't go for that. So we want to just point out the GPS down here as well. It's kind of hard to tell because these are only one data point per day, and this is basically measuring, in this particular plot, the distance across the caldera of Kīlauea. And so the distance had been spreading apart as magma was kind of building underneath there. As it relieved that pressure, it kind of sagged back down. It looks like we might have a little bit of an uptick back over here as well. That might correspond to the same inflation signal. It's hard to tell with the resolution of the data right in here, but that is something that could be happening. And you can kind of see the pool is also showing, it was looking like a more convincing signal is continuing to decrease here. Like it's looking like it's not the same thing as like what happened here, for example, right? Or what happened here, or, something like this, right? We just have to wait and see still. It's still kind of going, and that's something to kind of examine. We won't go into the GPS in any more detail today. Did that enough the last time. So if you want to know more about the GPS, go and check out our last update from a couple of days ago, how that all plays out. All right, so we've talked about other locations, the seismometers, and make sure that we do also cover the earthquakes that are happening. And so let's see here on Hawaiian Island, we just had the most recent earthquake is a 1.8. Here on the southeast flank of Mauna Loa, intermediate depth. Nothing to be alarmed about there, kind of just an adjustment. Imagine the whole island has to adjust all the pressure and the shifts that are happening through here, right? So there was an earthquake over here, 1.7, Captain Cook. That was earlier this morning, a little more than 12 hours ago, and Mauna Loa had a 2.2 in that kind of zone that it likes to, near the surface where it likes to sometimes put out little flurries of earthquakes. We have our Deep Pahala earthquake still happening over here. And we have 3 South Flank earthquakes. And that is it. And we don't see anything over here at Kīlauea Summit showing in our plot. Right, so that's fascinating as well. We're definitely not, whatever buildup of inflation, there's no pressure to put any earthquakes to actually happen. So, and with that, we can take our last round of questions here before we sign off. And what do we got, Dane?
Right. So, Jason Olsboot, oh my God, I can't even talk. Asks, is the lava possibly melting a hole deeper into the crater? Right, because we saw the pit that the collapse formed where the water was sitting. Then so could it go down deeper? Is the question.
It might be able to. It's basically, it's a question of the rate as everything else, right? So it's like how fast is it heating up, or how fast is it cooling off, right? Because at that edge, you could possibly having some remelting happening towards the rocks on the outside, but you'd have to have the gradient be really high and have to be really hot all the way down through the lake the whole way, right? And so because maybe that was happening in the early phases, right? In the early phases of lava going in there and swirling around, like as much lava was pouring into that smaller area where like radius was a lot smaller, and it was circulating through there, right? You might have had some physical erosion. You might have actually been able to put more heat into the walls, and maybe there you might have melted a little bit. But we're not talking about it melting that much, right? You're talking about probably on a scale of inches, and maybe if you combine a mechanical erosion of the actual liquid, but dense rock, even liquid lava is dense compared to water, so it can carve out and erode and wear out the bottom of a pit like that. The actual melting probably more in the order of inches, maybe a foot, if you had like a really huge effect. But I have to go through some calculations. That probably takes something extreme to get to a foot, I think. So maybe a little bit. Maybe it melted a little bit at the start, and since then it's been actually freezing and now has a rind of where it's cooled, because now heat's also going out the sides, right? It's not like this thing is ripping from the bottom, it's ripping from the top down, and heat can escape from the sides, although it's much more slow than coming out the top. Right, so.
Right. Chris Colby asks about the tilt in GPS signals. In particular, do you think that those signals indicate a continued eruption? or are going to indicate a continued eruption.
Yes, this is all the question of how long this thing tails off. It could. It's all about now that the rate has gone down, it could tail off for a while, right? But and especially now that we see the inflation signal that occurs locally at Uikahuna, we have that inflation signal. We know it's not like a whole summit inflation, because here is at eastern edge of the summit at Kīlauea not showing that kind of signal. We don't really see what's happening in the south right now. Our data is missing. At the escape road, you can kind of see that what we're interpreting as that backflow of lava back into the rift zone is slowing down, right? Right here, it's slowed down. It may be that it's equilibrated is one possibility, or it could be that there's more pressure building back up. It's kind of hard to say what the actual cause is there. So there is a chance that this thing draws out for a while longer still, right? We really don't know. So I won't be surprised if it draws out. I also won't be surprised if it starts sputtering more. Right, we have bigger, if that inflation is caused by gas, but big gas bubbles accumulating, for example, and they're not being able to all be vented fast enough, then maybe you have one big slug comes up and does something, and then once it's relieved, then you have a lower background rate again, and you might have that kind of pulsation kind of thing might be happening as well. So it is interesting. I see that as well. I see that this is definitely leveling off over here, right? So it's not like this is still emptying out continually, like something has changed a little bit over here, and it's not quite clear the dynamics, right? Pu'o'o, we now can actually see, is showing a tilt signal, also seems to be dropping all the way over there, right? So interesting as well. Now, for those of you guys worried about further down the rift, here's Jonica Station. We do not see anything like that at Jonica, right? Maybe a little bit, right? You do kind of see like a little bit of downward trend here, but in all, it's like a microradian, right? Pu'o'o is a little bit larger. We look at the scale in Pu'o'o, and let's take the 20th as a start without knowing what's happening right through here, right? But if we take it from right there, that's -2, and down here is -6. So it's dropped 4 microradians at Pu'o'o already, which is a number that definitely it's not like alarming, but it's like it definitely is something that deserves attention.
All right. So this one's kind of an aggregate question. I've seen it several times. I've also tried to answer it in the comments, but it just keeps popping up its head. 2 parts. First, how deep is the crater / the caldera, right? Because we have these different levels that we're talking about when we're talking about how deep it is, in how submerged this lava lake is. And secondly, this is the one I keep seeing: will lava escape the caldera?
Well, so will it escape the caldera? The easy answer is no. So let me bring up the Google imagery here. I'm going to give me this Esri imagery here on the back of the USGS map, right? So that's just what I'm going to use. So okay, this pit right in here is the lowest part. Then you have kind of a pit right in there. You have a higher cliff there. Then you have a higher cliff right in there. And you have another cliff that's right there. And then you have what most people consider the caldera wall, being this one right there. Right. So what you need to know is that on this side, this is the high side. It's something like 400 feet high, 100 meters. So like it's hard. You have to build up another 100 meters of lava across what is essentially 3 miles long here. That's a lot of lava to actually try to overtop
right.
This side, right? This lower ledge over here is actually lower. So maybe I can pull up my topo map. Give me just a second here.
And while he's doing that, just for like historical reference, like the last time the lava that I believe Phil can correct me on this, the lava was outside of the current existing caldera, was previous to the 1500 collapse. So we're talking like 1290 to 1470-ish era, where it was a shield, and then the 1500 collapse formed that caldera.
Yeah, that's about right. Yeah, exactly. The Southwest Rift does kind of intersect the caldera there, so there have been some eruptions in that area that kind of
Right.
start just outside that crack, and then they've run down the southwest rift before.
Right.
But that's different, right? So let me see if I can drop this in here for you guys. And yeah. So this is in meters, and so I can show you guys now down here that the south side over here is at this 1100 meter elevation, right? More or less. Right through there, right? If it were to spill out of the caldera, it wants to go out this way over here. There's kind of this low bay right over here. Not quite all on my map over here, but it kind of goes this way like that. Right, so it's really hard for it to get out of caldera. So let's go in a little more. Can it spill over this 800 meter contour line right in there? Well, lava is going to fill it up someday. This particular eruption doesn't seem like it has a vigor or the rate. You know, the rate of accumulation is essentially stabilized. It's not getting. So far, it has. You know, it got a little less deep. And then now got a little deeper again. We'll see what the trend continues getting deeper or not, but it doesn't seem like it's able to build more depth very easily. So all those projections we made before were all based on that initial rate, which is now no longer the case as we expected, right? But it was kind of a fun game to imagine, like, well, what about the next eruption? What about the one after that? What about the one after that? Where is it going to spill over? So the answer is the first place it's going to spill over is going to be this little ledge right over here when it gets to this 800 meter elevation. Then when it gets to 900 meters, it's going to spill over on this little ledge over here. But at that time, it's also going to be lapping up like all the way to there, like that, right? And then kind of going back around like that, right? Okay, so then once it gets a little higher than that, then it can kind of start spreading out in this flat area over here. This is that down drop block area. And once that actually happens, you might actually get some little rivers of lava kind of flowing this way or flowing that way, and, you know, doing some interesting things like that. Whatever eruption that happens to be, whether it's, you know, years from now or whenever it happens to be, right? You know, lava's not going to come up this high on this eruption unless something drastically changes, like some another huge batch of magma coming from below and just, you know, a whole new thing, a whole new chapter of the eruption, so to speak, right? Which is not something we anticipate. We don't see those signals. It's all localized, kind of like pressure's building just in the area, right? In there where this station feels it and this one over here doesn't feel it, right? So, maybe that's the answer there. It will not, you know, it will not escape the caldera for sure. The last time, lava was in the 1920s. We had a lava shield over here with a lava lake perched on top that was actually taller than this rim, and it still managed to not spill over. If that had kept going instead of the 24 explosion, maybe we would have had the first flow in centuries that actually escaped the caldera. But we missed our chance, and 24 was our best chance, and we kind of missed it. We're really far from that now.
Yeah, we're on the other end of it.
Yeah.
So final question I have here for you. Can you compare the current lava lake to the size of the Kīlauea eruption and that pooling of lava there?
Okay, so
Prep for this. Maybe just best pop out Google Maps and just, you know, use the pin.
Yeah. I can kind of show you. There's a couple ways to look at this, right? Because there's volume and there's area and there's depth and there's all different ways to look at it, right? So if you look at the actual diameter of Kīlauea here, what's going on with my zoom? It doesn't want to go anymore. Okay, so you know that Kīlauea diameter, it's actually really long going this direction, and you know not quite as long this direction, but still pretty wide. The width in the short axis is about the width, like up here, of this close to the 800 meter contour right in there, right? So our lake is not the size of that 800 meter contour, it's smaller than that. So as far as area, our lake has a smaller surface area than Kīlauea. And it's hard, you know, without doing calculations, I would guess by a factor of 4 or something like that. As far as the area. Now, as far as the depth, Kīlauea ended up being 440 feet deep. And we are now at, 570, 580 almost. So
right. I'd like to just see if I have this still up. I'm trying to find the measurements for how deep this one in cubic meters was. Estimates right now.
Right.
Stand
So
by.
I can get the update back up here. Let's see where my update is. Is it that one? Nope. Is it that one? That one says 21.5 million cubic meters.
Right. So 21.5 million cubic meters, and the was that? Do they have the gallons measurement? Because the one I'm looking at is in gallons. 5.6 billion gallons.
Okay, now this one's showing a little less. This one's showing 4.9 million gallons, so we must be above 21.5 million cubic meters on that gallons. But the volume of Kīlauea, I forget in the end now. I did have this open.
Right.
And a couple updates ago, I had this open. Let me see if I can find something here for you guys.
I keep seeing them broken down into the first phase of the eruption. It's, this many million gallons in this phase. But the cumulative total escapes me on that one.
Yeah, I have it somewhere. It's in this. Let me open this and bring you guys the. I got it coming, I promise.
It looks like 6. All right, so I'm finding a paper here from McDonald saying 61 million cubic meters in 16 eruptive events on Kīlauea.
All right, here we go.
Over the course.
So Kīlauea, that what actually was left in the lava lake was 38 million cubic meters, right? There was 60 that went back. So in total, the actual eruption, there was 71 million that came in from depth. And of that 71 million, 38 stayed on the surface at Kīlauea because there was also another intrusion that didn't cause an eruption, right? This might be similar to the one we had 2 weeks before, right? Although they're showing it as afterwards and timing wasn't the same. And they also had a Kapoho eruption that kind of took off the rest of that volume as well. So 38 million was the actual, the amount of, if you guys look at this cross section, the lava lake and the hill of Pu'upua'i that was left on the rim of the crater up there at 38 million cubic meters. And our USGS figure, if this one was 4.9 and they're adding another 10%, right, ish, then we're looking at on the order of, 23, 24 million cubic meters for this one. So 23 compared to that 38, we're what, 2/3 there, over 2/3 there. For volume, right? So for depth, we're deeper. For surface area, we're smaller. And for volume, we are still smaller, but getting there, 2/3 of the way there. All right, so thank you guys for tuning in. Thanks for checking out our broadcast. Just want to remind you guys we're brought to you by Hawaii Tracker, hawaiitracker.com. You can find us on the internet, also on Facebook. You can see we put our eruption updates up here. This is a place where if you do want to support our work, you can do that right over here in the donate button. And if you would like to advertise with us, we do have packages available for that as well. So anything else you'd like to add, Dane, before we sign off here?
No, I think that's about it. We thank everybody that, tuned in. We're trying to do this live now on Facebook, Twitter, and YouTube. So to all the different people in the different communities that we've checked out, our main one that we do work on is the Hawaii Tracker Facebook group and the hawaiitracker.com site, right? Those are kind of our main places for information right now. And yeah, come on over, check it out. With a lot of really interesting people that are, posting either photos that they're taking overflights of the volcano, all kinds of different information coming through there that we don't get really to share on this, stream. So yeah, check them out, and definitely appreciate everybody that took the time to stop in and, maybe learn something.
Right on. Thank you guys. Mahalo, everybody. For myself and Dave DuPont. Thank you guys. Aloha.
All right.